Okay, thank you, Ravi, for inviting me and the institute as a whole. It's a pleasure.
First of all, please share the screen.
All right, yes, just a moment. Okay, so everybody can see my slides.
Yeah.
Perfect. Okay, maybe I'll go to the full screen mode. Good. Okay. So thanks once again to Ravi Prakash for inviting me and to the institute as a whole. So
You are mute, Souvik. You are mute. Oh no, we cannot listen to you.
I cannot hear.
Yeah, me too. Me too. We cannot hear. Souvik, can you listen to us? You are not audible. Okay. स्क्रीन शेयर कैंसिल करके फिर से एंटर करो.
okay.
Now, perfect. It's okay now.
So what I will do, I will just share my screen, but not go into the slide presentation. Maybe.
Yeah, maybe.
That's creating some problem. Okay, let's see. Okay, so everybody can see my screen, the slide. Okay.
Now, yes.
Okay. So I
can see.
Okay. So all of you can see now?
Me,
Yeah,
yes.
yeah, yes.
Yes.
Okay. Yeah, so I'll keep it in this mode and don't go into the full screen mode. Maybe that's the problem. So the topic of today is algebraic cycles. So at the very base level, it's using linear algebra. But of course, linear algebra is used in different fields. So I'll be using it in algebraic geometry. Okay, so broadly, there are three topics today. So Chow groups and a filtration on the Chow groups, height pairing, which we will have some time to discuss. And the new idea is only if time permits. So the main point is to give an expository idea about Chow groups and height pairing. Okay, so let's fix the notations. So small k and capital K or capital K, this will denote subfields of C, the complex number. And a number field is a finite extension of Q. So for example, you can attach the number root 2 to rationals to get an extension of Q, so that's an example of number field. Or you can, for example, attach the imaginary number I to Q to get a finite extension again. So that's an example of another number field. So there are various number fields by attaching irrational numbers to, or rather algebraic numbers to Q. So for any number field, there is a number ring inside it. So we will denote the numbering with this notation. And if we don't specify otherwise, X will always denote a smooth and projective. So I have to start at some base point. So I assume that everybody has some knowledge of this, or at least what manifolds are. So if you are not very comfortable with a smooth projective variety, just think of compact and complex manifolds. So that will more or less give you an idea of what's going on. Then for a finite dimension, so this is another convention or notation that we're going to use. So given a finite dimensional vector space and a subspace, we define the codimension of the subspace to be the difference between the dimension of V and the dimension of the subspace. And of course, this makes sense whenever we are dealing with finite dimensional objects. For example, if you have a manifold, which is finite dimensional, and a submanifold, then you can talk about the codimension of the submanifold. Similarly, for algebraic varieties, so mostly we will stick with the algebraic varieties. Okay. So first, so there are two objects that will come into play here. So number one is the cohomology of a smooth projective variety. So associated to a smooth projective variety, we have a complex space. So this complex space associated to X is a compact and complex scalar manifold. So given, just assume for the moment that it's a compact and complex manifold. So for such manifolds, we define, well, for any topological space, we can define the singular cohomology of that topological space with rational coefficients. Now, for any compact and complex manifold, we also have de Rham cohomology of X. Now, this isomorphism is true for any compact and complex manifold. Now, given any Kähler manifold, so this is where the Kähler condition comes into picture, you can decompose such cohomology groups of the manifold into PQ forms. So here, these consists of the space of D-closed PQ forms, of course, modulo co-boundaries, with the following property that if you complex conjugate, so it's over C, so if you complex conjugate, then you get the QP. So if you complex conjugate the PQ forms, you get QP forms. For example, you can take, let's say, X is P1, the projective space, and you can take DZ wedge DZ bar. Okay, so then if you take the complex conjugate, you will get DZ bar wedge DZ. So such things. So DZ wedge DZ bar is a 1-1 form. Okay, so any compact complex scalar manifold has such a PQ decomposition. So that's the cohomology part. Well, not completely. We still have the Hodge filtration. So given the de Rham cohomology of X, we can associate a filtration to it. So again, think at the very base level. So all of these are vector spaces over C or over Q. So an important way to study any vector space, let's say finite dimensional vector space, is through filtration. So if you can filter a vector space, let's say if you can define a decreasing filtration on a vector space, then by studying the parts of that filtration, you can hope to study the whole vector space, right? So in the same way, we define a filtration. So it's the same idea. So we define a filtration, a decreasing filtration on the Rth de Rham cohomology of X with this decomposition. So FI-HR is, we take the PQ parts where P is greater than or equal to I. Okay, so this defines a decreasing filtration. We call it the Hodge filtration. Okay, so this is the cohomology part, but the main part of today is algebraic cycles. So what are algebraic cycles? So for cohomology of X, we needed to go to So if you recall, we needed to go to this complex space and we needed to study the differential forms on this complex space. On the other hand, to study algebraic cycles, it's more intrinsic. So we stay on X, which is an algebraic variety, and study subvarieties of X in the following way. So let the small zr of X denote the free abelian group generated by subvarieties of codimension R in X. So the dimension of the subvarieties is dimension of X minus R. So we call an element in this an algebraic cycle. Okay. Now, if you just work with this particular group, then it's too large. So it's a free abelian group generated by. So there are infinitely many subvarieties of codimension R inside X. So this group itself is inadequate. Inadequate in the sense that it's not good just studying this group. What we want to do is to quotient this group by a suitable subgroup so that we have a ring structure on the resultant group. So that's what we do. We quotient out this free abelian group by a suitable equivalence relation. So we call this a rational equivalence. So again, a very rough idea, two algebraic cycles are rationally equivalent if they're parametrized by a projective line P1. So one can go from one algebraic cycle to another through the projective line in some sense. So if one knows homotopy, so it's in one sense homotopy between one cycle and another by P1. So we denote the subgroup of cycles rationally equivalent to 0 by this notation. And we define the Chow group of X to be the quotient. So we quotient out this huge group of codimension R subvarieties of X by this subgroup of rational equivalence. The good thing about this particular group, there should be a CHR of X, is that this group has a ring structure. So if you take one subvariety of codimension R and another subvariety of codimension S, then you can intersect them and get a new subvariety of codimension R plus S in a particular way. I mean, it's not so easy as just intersecting. So this part of intersecting two subvarieties is actually a book by Fulton called Intersection Theory, where he developed this whole idea of algebraic cycles and this ring structure. So anyway, so we have to quotient out by this rational equivalence to get a nice ring structure on this group. Okay, so on one side we have the Chow group, and on the other side we have the cohomology group. You can keep this example in mind for Chow group of 0 cycles. So it's an important subgroup, important free abelian group to study. So ZD, so a D is the dimension of X. ZD of X consists of free abelian group of points in X. So recall that codimension D means dimension is D minus D. So the dimension is 0. So they are just points. So points on X. Okay. And this is just a convention that we use. So we use the rational Chow group. So we treat this group as a vector space over Q. So we simply tensor with Q. The idea is that at least for what I do, I don't need the torsion. But again, as I wrote, it doesn't mean that torsion is not important. There is a separate study of Chow groups, torsion algebraic cycles, but that won't come into picture today. Okay, so far, any questions?
Clear so far.
Clear so far? Okay, good. Great. So as I was saying, on the one hand, we have the Chow group, and on the other hand, we have the cohomology group. So what exactly are we doing if we, so this was the idea of the great mathematician Grothendieck, Alexander Grothendieck. So he envisioned that, so you have this category of smooth projective varieties over K on one hand, and on the other hand, you have the vector spaces over Q. So this Chow group or the cohomology group, let's say the singular cohomology group, so these are, in his words, they are realization functors. So you have a vector space, you attach the singular cohomology of X, which is a vector. You have a smooth projective variety. You attach the cohomology group, which is a vector space. You have the smooth projective variety. You attach the Chow group, the rational Chow group. So it's again a vector space. So in this way, we are attaching different realization. We are attaching different objects from one category to another. So what Grothendieck envisioned is a theory of motives. So I won't go again into that picture, where so he envisioned that there should be a big functor in that sense, a big category of motives, such that all these cohomology groups or Chow groups, they should come up as a realization functor of that category of motives. So I mean, Grothendieck has this, like, he was not a person to study objects in isolation. So he always used to study objects and functors between the objects. So the functors are more important to him than the actual objects. Okay, so in this case, what happens is that the cohomology of X is more well-behaved than the Chow group. So for example, the singular cohomology groups, they are finite dimensional vector spaces. So as a natural desire, one thinks that whether the Chow groups and the cohomology groups, they're somehow connected by some map. Okay, so if you can find a map between the Chow group and the cohomology groups, then one can hope to study the Chow group using the information from these maps. So indeed, what one thinks to be, okay. Well, this is always a general theme. I don't know why I put it here. I mean, this is the general theme of the talk. So the important thing is to detect non-zero cycles, algebraic cycles, using the theory of vector space or linear algebra. So you're using linear algebra, and to do it properly in this context, we have to develop some non-trivial machineries. Okay, so as I was saying, there should be some maps between the Chow group and the cohomology group, and indeed there are. So the first such map is given by the so-called fundamental class. So if you have an algebraic cycle here, forget about algebraic cycle, just think of a manifold and a submanifold, okay? Then you can define the fundamental class for that submanifold. So what is a fundamental class? So you just integrate forms on that submanifold. So that will give you a cohomology class, which you call the fundamental class. So given a subvariety, you can define the fundamental class, which gives you an element in the 2R de Rham cohomology of X. So this is a little bit of detail. So it not just land on the 2R cohomology group, it actually land on the RR part of the cohomology. Okay, so it consists of forms which have R holomorphic and R anti-holomorphic part. So equally distributed. So as a typical example of the cycle class map, you can take the following. So you have the Chow group of zero cycles, right? So the Chow group of zero cycles, they consist of points, so sum of points. So here. Yeah, so this is the definition of zero cycles. Again, you quotient out by the rational equivalence to get the Chow group of zero cycles. So here is a zero cycle. So alpha I, pi is are the points, and alpha I are just the coefficients. You simply send it to this rational number, summation alpha I. So this is a typical example of the cycle class map. So this is the summation alpha I. This is called the degree of this particular algebraic cycle. Okay, so far so good. Now, one cannot escape any talk which has cycle class map without mentioning the Hodge conjecture. So associated to this cycle class map, there is this famous Hodge conjecture. So it is one of the millennial problems. So the cycle class map, so you have the cycle class map which lands in this particular group, okay? So what the Hodge conjecture claims is that this particular map is surjective. Okay, so Hodge had different evidence. So he had many examples where this the cycle class map is indeed surjective, and of course that's what I mean. That's how he came up with this conjecture. But he had no further clue. I mean, he had no further, let's say, intuition other than those examples. Later, was it later? So I'm very bad with the number, I mean, the years, I don't know. So Lefschetz already proved this this particular theorem for r equals 1. So ch1 of x with rational coefficient surjects to h11 of x comma q. So Lefschetz already showed that, and not just for rational coefficient, also with z coefficient. So forget about tensoring with q. He also showed this for the torsion case. So in some sense, it's even stronger. So but Lefschetz, I think he didn't knew about Hodge conjecture, and later it was, I mean, people probably told Hodge that the case r equals 1 is already done. But of course, for r greater than 1, there are plenty of obstacles for this conjecture. So we will leave it at that. We won't deal with this conjecture anymore. There are many cases where this conjecture is true, but the general case is open, of course. And people are trying this with several techniques. That's the beauty of this conjecture. So very recently here in a talk, I heard about one attempt of this Hodge conjecture using tropical geometry. So many different fields are coming into picture to solve this conjecture. But for the moment, they're not completely successful. Anyway, since we are in the cycle class map and coefficients, let me mention about the following, and we will use this later. So algebraic cycles, we generally regard them as having weight 0. So what we mean by weight is that all these cohomology groups that we are studying, they are examples of what are called mixed Hodge structures. Okay, so given a vector space, one can associate a mixed Hodge structure. I mean, not all vector space, but a mixed Hodge structure is associated to a vector space. So it has a weight filtration, which is increasing, and a Hodge filtration, which is decreasing. So it has two filtrations. So we regard algebraic cycles to have weight 0. So they land in the weight 0 part of the mixed Hodge structure. So in this case, the mixed Hodge structure is this, the cohomology group. One basic example of mixed Hodge structure that we want to keep in mind is the following. So this is called the Tate twisting of the rational. So we simply multiply the rationals with this 2 pi I to the s factor. So this is a one-dimensional Q vector space, and we regard this as an example of a mixed Hodge structure, or rather a pure Hodge structure of weight minus 2s and type minus s comma minus s. And then we define the cycle class map as having value in this particular homology group. So all we are doing is not just taking the fundamental class for the subvariety. What we are doing is we are adding suitable multiples of 2 pi I. Okay, so on the face of it, it's useless. So why would one do that? So that's the comment here. So for topologists, the fundamental class is enough. But if you are an algebraic geometer, this weight, the adjustment of weight is really important. Well, I mean, algebraic geometer or complex geometer, these weights come up naturally, and adjusting the weights and treating algebraic cycles to have weight 0 is vital. Okay, so that's about that. So cycle class map is one important map between the Chow group and the cohomology. The second map is the Abel-Jacobi map. So you'll see how the vector space structures come into picture. So given this cycle class map, of course, this map is not injective. There are plenty of examples where this can be 0. Even, for example, if you take this particular map, you can play around with coefficients. For example, take x equals, let's say, p1 again, and take 2 points, let's say r and s on p1, and take their difference, r minus s. Okay. Well, r and s are not very good notations. Let's say q1 and q2, 2 points on p1, and simply take their difference, q1 minus q2. So that is an algebraic cycle, right? So it's an element of the free abelian group. Through this map, where does it go? It goes to 1 minus 1 equals 0, right? So a non-zero element, p1 minus p2, goes to 0 here. So the cycle class map is, of course, not injective. So let's call the kernel of the cycle class map with this notation. So these are called cycles homologous to 0 on X. Okay, again, a typo. So either call it null homologous or homologous to 0. This term homologous to 0 comes from the homology, of course. So this is the point. So suppose you have an element which is homologous to 0. So of course the image is 0 in H2R of X. So using Poincare duality, this eta can be seen as a boundary of a membrane, chi can be seen as a boundary of a membrane eta. Okay, so this eta is a real 2D minus 2R plus 1 dimensional chain with rational coefficients. So just something to keep in mind. So we are using Poincare duality. Poincare duality in the sense H2R of X comma Q is isomorphic to 2D minus 2Rth homology of X. And being 0 in the cohomology means 0 in the homology. So it's 0 also in H. So it's 0 at the level of 2D minus 2R. So then there is this chain eta. So it's a 2D minus 2R plus 1 dimensional chain whose boundary gives you this chi. Okay, so just keep this in mind for the moment. Well, so this also plays a role in developing this Abel-Jacobi map. So using this above with this information that this is the boundary of a real dimensional chain, and again a little bit of Hodge theory, we can define the so-called Abel-Jacobi map. So the Abel-Jacobi map is from this Rth Chow group of cycles homologous to 0 to a certain group which is a compact and complex torus. So this is called the Griffiths intermediate Jacobian. So, I mean, I'm not going to explicitly define it, just know that this is a compact complex torus. And again, Griffiths was the guy who came up with this definition. So Griffiths actually, to me, is one of the most important complex geometers who developed this theory a lot. So if you are interested in complex algebraic geometry or algebraic geometry as a whole, you should study Griffiths' book, the Griffiths and Harris Principles of Algebraic Geometry. I mean, that's like a dictionary for all these things. Okay. In the special case where the codimensions are 1 and d, so 0 cycles, and so 1 are the divisors. So there's J1 and JD. These are the dual abelian varieties. So these are abelian varieties which are dual, but for general R between 1 and D, these are just compact and complex torus. These are not abelian varieties. Okay, so why this Abel-Jacobi name? Because if you take a smooth projective curve, then AJ1 from CH1 Hom of C to J1 of C, which is an abelian variety, is simply the Abel-Jacobi map. So what does one do here? So again, take the favorite example, C equals P1. Take 2 points, P1, take the difference of 2 points, let's say P1 minus P2. So that's a cycle which lands here. So how does one define the Abel-Jacobi map in this case? Simply take a suitable differential form omega and integrate from P1 to P2. Okay, so that will give you the description of the Abel-Jacobi map, and that's the classical elliptic integral. And I mean, that's the reason for this name. So it's a generalization of the classical elliptic integral. Okay. Checkpoint. So what exactly are we doing for the moment? We have the Chow group of X, and we have the kernel of this map. We call this the Chow group of cycles homologous to 0. As I said before, a very useful technique in vector space theory is to capture non-trivial elements via a decreasing filtration. So the idea is, can one define a decreasing filtration at the level of Chow groups, much like the decreasing filtration for cohomology? Okay, so that's the big idea. And it's not so easy. In the cohomology theory, it's easy because we know that the cohomology groups are finite dimensional and it has this PQ decomposition, so one can define a decreasing filtration. Not the case for Chow groups, unfortunately. So let's do some decent attempts. Let's declare the first candidate for the filtration. That's, I mean, the stupidest candidate, so F0, to be the Chow group itself. Then for the first piece of the non-trivial piece of the filtration, one has this candidate, the Chow group of cycles homologous to 0. Okay, so let's just declare these are the two pieces of the proposed filtration. And again, a notation, so we call the quotient by this notation. So these are the graded pieces of the filtration. Now, notice that through the cycle class map, the GER0 piece of the filtration injects inside the RR cohomology group, right? Because you have the cycle class map, which goes to HRR. The kernel of the cycle class map is precisely cycles which are homologous to 0. So GER0 injects inside HRR. Okay, so then what about the other pieces? So what about F2 and in general the other pieces? Again, one can play the same trick. So we have this cycles which are homologous to 0. Then we can define F2 to be the kernel of the Abel-Jacobi map. Again, the Abel-Jacobi map that we defined here, this is not injective. So it has it should have a kernel a priori. Okay. So just define F2 as the kernel of the Abel-Jacobi map. Then to do this, one should know that the Abel-Jacobi map is injective or not, of course. For R equals 1, the Abel-Jacobi map is injective. So, CH1 Hom is actually isomorphic to the abelian variety of X. But for R greater than 1, no. The answer is no. For K equals C, there are plenty of counterexamples. None of the counterexamples are, so this is one caveat. When I write that there are plenty of counterexamples, what I should say that none of these counterexamples are easy to define, and each one of these counterexamples form one paper. Okay, so there is a famous counterexample due to Mumford, general theory which gives plenty of counterexamples by Green, Griffiths, and Paranjape. My supervisor, James Lewis, he gave some counterexamples for, he gave examples where this map is not injective. So there is indeed a kernel as long as you take K to be the complex numbers. Here I mention one folklore conjecture by Bailinson. Folklore means nobody knows how Bailinson came up with this conjecture. Maybe it's just kind of a fever dream. Like he had some idea. Bailinson has some crazy ideas sometimes, and I think the history of this conjecture is that he needed it for some part of his paper, and then he mentioned this as a conjecture. It's more a wish than a conjecture. So what is that wish? The wish is that if you take, instead of the complex number, if you go to the other spectrum, you take a number field. So then is the Abel-Jacobi map injective? So that's the conjecture. That if X is defined over Q bar, so Q bar is the field of algebraic numbers, or forget about Q bar, just take a number field for that matter, then the Abel-Jacobi map is injective. That's the conjecture. The problem with this conjecture is that there are no examples where, there are no known examples where this holds. So it's extremely, extremely difficult to get an example, and forget about counter examples. So even an example is elusive. Okay, so if anybody wants to work in this subject in future, avoid this sort of conjectures. Don't fall in trap. This conjectures, once you study the subject, is very tempting. So please avoid it during your PhD studies. Yeah.
Can I ask? But
yes.
Just, for example, if you take the projective space, then the structure of the Chow group is it is generated by the class of a hyperplane, and this intersection. Right there, everything is known.
Yeah. Exactly. For Pn, the projective n space, everything is known. Yes. Mm-hmm.
Okay, so you want to exclude in remark 012 something like rational varieties or something like this?
In remark 12, I want to. You mean? So if you take Pn over a number field,
yes,
then
the map is injective, no? Is that what?
Yes.
Or maybe I'm confused. But
if you take X equals Pn, for example, then first you have to see what are the cycles homologous to 0. Right. So the Chow group is given by the hyperplane. So it's Z. It's Q. The Chow group is Q. Then Yeah, but it can still have cycles which are homologous to 0. I mean, this map is from this, the double Jacobi map is from cycles homologous to 0 to the Jacobian.
Yes, but I think in that case, the two domain and codomain are trivial, so it's injected, is a 0 mapping to 0.
I mean,
unless I'm missing something, it could be that I'm missing something, but I would say that the rational cohomology of the projective space is just like the Chow group. It's an isomorphism in any degree. So
yeah, in any degree, it's an isomorphism.
yeah.
Oh, I see. Yes. Yeah, exactly.
Okay. So.
Yes, exactly. Okay. So let's get back to filtration. So let's take K to be complex numbers, not number field. Or, well, I mean, in general, the Jacobi map is not injective. So going back to the filtrations, so what could be F2? Okay, so let's say that F2 is the kernel of the Jacobi map. Then to define further filtrations, what we need to do is to define a map from F2 to certain groups, okay, which generalizes the cycle class map and the Abel-Jacobi map. The question is there is there a category whose extension groups generalize the Jacobian? Okay, so again, the mixed Hodge structures, they come into picture, and that's indeed the group which generalizes the Jacobian, in the sense that if you take X1 in the category of mixed Hodge structures of Q by this particular cohomology group, so H2R minus 1, this is indeed isomorphic to the to JR. Okay, so this is indeed isomorphic to this. Okay, so this group JR, the Griffiths intermediate Jacobian. So since we have declared the F1 of CHR to be cycles homologous to 0, we can write the Abel-Jacobi map as the map between F1 of CHR to X1 of the mixed Hodge structure. Again, it's a non-trivial result. The non-trivial part is the isomorphism between this group and Griffiths intermediate Jacobian. So this was shown by Jim Carlson. Okay, so but there is a problem. The problem is that the category of mixed Hodge structure has this property, again a non-trivial property shown by Deline, that the X groups vanish beyond 1. So X2 onwards is 0. So even if we want to define a map from F2 to X2, it won't give us anything. So it will just give you back the whole group F2, since this is 0. So it won't capture non-trivial cycles inside F2. So just again a passing remark, that there is a generalization called the conjectural category of mixed motives due to Beilinson and Bloch. And if you work with the X groups in that particular category of mixed motives, then one can indeed define maps from certain subgroups of the Chow groups to that category of mixed motives. Okay, so now let's give you a semi-formal definition of what we want for the filtration. So a conjectural decreasing filtration on Chow groups is of Bloch-Beilinson type if it satisfies certain properties. And the most important of these properties is the finiteness property. So the filtration should stop at certain point. To be more precise, Fr plus 1 of CHR should be 0. Okay, so it's very precise. The filtration, the conjecture says that the filtration shouldn't go beyond level R. Okay, and there's a reason for that, right? Because if you want to study a vector space, and if you want to study it through filtrations, you want that to stop. Otherwise, you cannot capture all the elements. So that's the reason why the filtration should stop. And once again, outside smooth projective curves, hardly anything is known about this filtration. For abelian varieties, there is an incomplete filtration. So for all such filtrations, the most important part is that the finiteness property, and that finiteness property is still elusive for any example beyond curves. So even though there are no, there is no filtration as such for the moment, there are several candidates for such filtrations, and each of those candidates are important to study in their own right. So Morihiko Saito, Green and Griffiths, my supervisor James Lewis, they gave different examples of such filtrations. Well, different examples of such filtration, with the caveat that all this filtration failed in the finiteness property, which it doesn't mean that these filtrations are not important, but keep in mind that they fail in this vital property, but they have their own merits. So using these filtrations, we can study the Chow groups up to a point. Okay, so in some sense, the graded pieces of the filtration are more important than the filtration itself, in the sense that we have a non-canonical decomposition of the Chow group using the graded pieces. So, and sometimes it's, not just because of this reason, sometimes at the level of cohomology theory, you will come across examples where the graded pieces are easy to find rather than the actual filtration. So you can know the filtration modulo the next piece, but not the whole filtration. Okay. Anyway, so this is more or less everything is conjectural with some examples as such. So filtration was one part of studying algebraic cycles. The second one is bilinear pairing. Again, if you have a vector space, you have and it's good to study bilinear pairings between vector spaces, right? So, for example, the non-degeneracy property of such a pairing would help in detecting non-trivial elements in a vector space. So, as a first example of bilinear pairing, what one can do is take a codimension R cycle and take a codimension D minus R cycle, so complementary codimension, and intersect. So what you get on intersecting is a bunch of points. So it should have codimension D, so it's a bunch of points. It will give you a number, okay? So this is the first example of a bilinear pairing between two Chow groups in complementary codimensions. Okay, and it's an important example to study. So this particular pairing, it filters through Chow groups which are homologous to 0. So if one of the cycles is homologous to 0 here, then the product goes to 0. Okay. The reason being that this product, it factors through the cohomology. So you can also view this as the cup product in cohomology. Okay, so we have a pairing at the 0th graded level. Recall that curve 0 is CH mod CH hom, at least conjecturally. So we have this bilinear pairing. And it's an important pairing in the sense that the primitive part, the so-called primitive part of this pairing is non-degenerate, at least for subfields of C. But in general, this is one of Grothendieck's standard conjecture. So for characteristic P, this is still open, whether this pairing is non-degenerate or not. Okay, good. So we have reached the height pairing part. So once we have this pairing at the level of Chow groups, you see that the problem here is that this pairing doesn't detect cycles which are homologous to 0 because it simply takes them to 0. So is there a way to define a pairing at the level of Chow group of cycles which are homologous to 0? So instead of CHR, you want to take CHR hom and a suitable complementary codimension against CHR hom of cycles homologous to 0 and try to define a pairing. So that's where Bailinson came into picture. So what he did was to define a pairing between Chow group of cycles, Chow group codimension R cycles homologous to 0, and this dot is a suitable number, which is the complementary codimension in this case. So this dot is actually D minus R plus 1. So the pairing is between codimension R cycles homologous to 0 and codimension D minus R plus 1 cycles, which are homologous to 0. Okay. Again, if you just take the usual intersection product, it goes to 0, right? Because these are cycles homologous to 0. So you have to devise some other techniques to get a non-trivial pairing on these two Chow groups of cycles homologous to 0. So let's make an attempt of how we can try to define a pairing like this. Let's take two cycles which are homologous to 0 and in this particular codimension. So what does homologous to 0 means? It means that this goes to 0 in this cohomology group, of course. By Poincare duality, this is isomorphic to this particular homology group. And as I said before, so then this is a boundary of a 2D minus 2R plus one dimensional chain. Okay, let's call this capital Chi1. So for Chi1, we have this 2D minus 2R plus one dimensional chain. Now for Chi2, the class is again 0 here. So remember that Chi2 is a cycle here, right? So it goes to 2 times D minus R plus 1, but it's 0 here. What does it mean to be 0 in cohomology? It means that there exists a 2D minus 2R plus 1 degree differential form, let's call it eta 2, such that D of eta 2 is Chi2, okay? Now, you know that you can integrate 2D minus, you can integrate R form against a R chain, right? So you have here a 2D minus 2R plus 1 form. So why not integrate against this 2D minus 2R plus 1 chain? Of course, one can do that. And this gives you a number. It gives you a real number, okay? We can declare that this is my pairing, just like that. So given two cycles which are homologous to 0, just declare this to be my pairing. Of course, there is a problem with this pairing, that this pairing is not well defined. So it depends on the choice of this cycle or this form. Okay, so it's not well defined. And moreover, we want a pairing at the level of Chow group. What we are doing here is defining pairing at the level of algebraic cycles. So this is a good attempt, but wrong. But again, it's instructive and something to keep in mind. At this point, I would ask, how much time do I have?
Yeah, 5 minutes, 5 to 10 minutes.
5 to 10 minutes. Okay, good.
Yeah. Okay.
Thank you. Okay, so this is the first attempt towards the pairing. Again, this is the caveat. The caveat is that if X is defined over a number field, one has to be a tad careful defining the cohomology of X, because K has several embeddings. It's a number field, so it has different embeddings inside C. So the complex space associated to C should incorporate these embeddings. And the second part is exactly what I was saying, that if you, well, it's another aspect of the pairing that I tried to define. What we did here, even though X is defined over a number field, what we did here is simply use the homology theory, right? So we used the complex structure on X and nothing else. So the fact that X is defined over a number field didn't come into picture at all. So I mean, this doesn't capture in generality the whole of X in some sense. So X is defined over a number field. So the primes in the number ring of the number field should play a role, but in the pairing that we have defined, it didn't. So one can call it, let's say, the complex part of some pairing or a complex pairing, but it's not really a total pairing. So again, so Bailinson was the guy who defined the total pairing. And to define the total pairing, again, we need to go into a subject. I won't, this is something one can talk over a semester course. So there is a theory by Gillet and Soule. It's called, Gillet and Soule and several other people. Of course, Arakelov was the first person to define this, the Arakelov geometry. So what does Arakelov geometry do is that it studies, given a smooth and projective variety over a number field, the point is that suppose we can spread this out to a regular scheme, which is projective and flat over the number ring of X. I mean, if you don't know, just stick to, the thing to take out of this lecture is this particular pairing. So this is more or less the highlight of this pairing. What I'm saying for the next few minutes would be just, a little bit abstract and more information than anything else. So one can spread it, suppose one can spread out to this nice enough scheme. By spreading, I mean that the fiber of this chi at infinity, at the generic point, sorry, of S is isomorphic to this smooth projective variety over K. So again, since spec of the number ring of K has cruel dimension 1, for nice enough schemes, again, this has cruel dimension D plus 1. Remember that D was the dimension of this smooth projective variety. So what one does is that there is a theory of Chow groups of those schemes. And then what Gillet and Soule did was to attach data at infinity with the Chow group in some sense. So the data at infinity is the data associated to the complex space of X. So they are given by green currents associated to an algebraic cycle. So the algebraic cycles of the scheme, together with this data at infinity, form the so-called arithmetic Chow groups. Now, of course, the arithmetic Chow groups, they have an intersection product and the so-called arithmetic degree. So it's, again, so you can think of this as zero cycles, the arithmetic zero cycles, and you can define an arithmetic degree. So one has a pairing. So if you take a codimension R arithmetic cycle, codimension D minus R plus 1 arithmetic cycle, you can define an arithmetic pairing to the set of real numbers. So all I'm going to say is that if suppose you have an X which has a nice enough spread, then you can pick two cycles which are homologous to 0 and complementary codimension. And there is a way to spread the cycles out to this particular arithmetic Chow groups. Okay, so then one defines Bailinson-Thite pairing simply to be the pairing of these spreads. Okay, so this bracket is the pairing between the spreads. Again, it's completely vague. I mean, one has to know the whole theory here to understand what's exactly going on. And this is the remark that, of course, one has to check that this pairing is well defined. And further, the bigger issue is that given a smooth projective variety, one doesn't know that whether one can spread it to a nice enough scheme. So that's the bigger problem, even before defining such a pairing. So for nice enough examples like abelian varieties, one can do this. One can play this game. So for abelian varieties, for example, one can concretely define this Bailinson pairing. Again, not much more is known. So there are examples. So you take triple products of curves. For that, this spreading is known. Okay, so this is fine. So the point is that all this sort of intersection products that we have defined, they are secondary level intersection products. So the primary level intersection is just intersecting two elements in the Chow group. Here, one of the element is homologous to 0. So you have to spread that out. So in the sense that this is the boundary of a membrane. So it means, for example, if you have a 3 space, and suppose you have two cycles which are two curves which are homologous to 0. So one curve being homologous to 0 means it is the boundary of a surface. And then one can ask how the other line intersects this surface. So this is basically the philosophy, at least the complex part of the pairing. Okay, so again, this is something not really important. So what I did afterwards is to generalize this Bailinson site pairing to higher graded pieces of the filtration. So I took one particular filtration given by James Lewis, and then I tried to define a pairing which is akin to Bailinson's pairing, but for the higher graded pieces. But I won't go into that. I don't have time for that, and it's too technical. So thank you, Sean, gracias, and I'll stop.
Thank you very much, Souvik. Anybody has question very quickly because we have just 2-3 minutes.
No, more or less, I just want to thank Souvik for this observing talk, but I think Anthony has a question.
Yeah, Antonio,
yes,
please.
Thank you. You introduced two things. One is the direction, which is conjectural, if I got it correctly, and the other one is the pairing.
Which conjecture?
Okay, so, sorry?
Which conjecture?
No, you said that there is a possible filtration, but
Right.
It's not known if there is one with the properties that you proposed.
Right.
Okay.
Right, yeah, so, the filtration is conjectural, yes.
Okay, so then the purpose, if I got it correctly, this last one, was to produce a pairing between the pieces of this filtration.
Yes.
This
is not conjectural. The point is that, if I understand you correctly, the pairing that I produced is not conjectural because I took a particular filtration. So as I said before, that different mathematicians gave some candidate filtrations, right? And each one of them has their own importance.
Okay.
So I took one such filtration. So the one given by my PhD supervisor, James Lewis. So, I mean, that's one of the filtrations that's been widely used. So I took that filtration. So, I mean, this pairing that I defined is not conjectural. So that's the point. So I took this particular filtration by James Lewis. I don't call it the Bloch-Bailinson filtration. So let's call this the James Lewis filtration. So I defined the pairing on that particular filtration.
Okay.
Does that?
So another very just vague question. I was expecting you could produce new cycles via this method. Did I got it correctly?
Not new cycles, not new. The thing is that even detecting, so suppose you have a Chow group, okay?
Okay.
And I just give you an arbitrary cycle. Suppose, let's say, I mean, you can just work on projective variety. So let's say I arbitrarily give you a cycle, okay? And ask you whether this cycle is 0 or non-zero, okay?
Okay.
And it's really very difficult to say whether that cycle is 0 or non-zero just using, I mean, just staying at the level of Chow groups. Okay. So that's when one goes into all these maps. So one defines the cycle class map, then the Abel-Jacobi map to detect the cycles, basically. Yeah.
Okay.
Mm-hmm. I mean, detecting whether a cycle is 0 or non-zero is an important exercise in algebraic cycles.
Okay.
Yeah.
Thank you. Thank you.
Okay.
Very nice.
Yeah. Thank you, Souvik. So we have to close it here, and
sure.
Thanks again for such an interesting talk. I hope everybody enjoyed.
Yeah. I mean.
Okay.
Yeah.
Of course,
so,
yes. I'm
send,
not asking you. I'm saying you.
No, I know. So I will send you the slides, Ravi, and if anybody is interested, they can see the slides.
I will distribute it. Sure. Fantastic idea.
Okay. Good.
You can stop the. I'm going to stop the